Howdy. We're going to be taking a look at Chapter 5, problem number 21. This is a fairly involved problem, so I'm actually going to make this a little bit more interactive. At points during the process, I'm going to ask you to pause the video and to do a little bit of work yourself, and then compare that to the work that I do. And in this way, I think that you will understand and learn the problem a little better than you would simply by watching. In this particular problem, we are told that a curve is perfectly banked for a car traveling at 75 kilometers per hour. And now they want to know what the coefficient of friction is required in order for a car to be able to travel at 95 kilometers per hour. So we have to find mu so that the car can safely travel 95 kilometers per hour around it. We were also told that the radius of the curve is 88 meters. Now, the first thing that we observe is that the speed that they give us are in kilometers per hour, which we consider to be kind of useless because we're used to either miles per hour or meters per second, but kilometers per hour, not so helpful. So the first thing I'm going to ask you to do is to convert the 75 kilometers per hour into meters per second, and the 95 kilometers per hour into meters per second. And at this time, please pause the video and do those two computations. Welcome back. What I got was 20.8 and 26.4 for these two speeds. Okay, well, let's get a picture of what we're looking at. If we do a top view, and we're looking at a car going around a curve like this. Now, probably in real life, the road would not be a perfect circle, but instead, we would just have a portion of a circle. So maybe the road has a little bit of an arc, just like this. And the radius of the arc is 88 meters. And now the car is going to be traveling with a speed of, well, in the first instance, it's going to be traveling with a speed of 75, excuse me, we did all that work, we need to use it, of 20.8 meters per second. And in the second instance, the car is going to be traveling with a speed of 26.4 meters per second. So in terms of problem-solving strategies, you recognize that we have a before and after, or a two-stage kind of problem, two-step kind of problem. In the before step, we're going to determine something about our curve, and in the after step, we will actually find the coefficient of friction. Let's take now a side view so we can see what's happening. If we look at the side view, then our curve, or this portion of it, is going to look something like this. The car is going to be traveling around the circle in this way. As we see it from the side here, we can see that the curve is banked so that it helps to support the car, helps to keep it moving in that circle. Now, the words perfectly banked mean that the car will be able to travel around the curve without the assistance of friction. Normally, when a car goes around the curve, the tires grip the road, and that frictional force pushes the car in a circle. But here, the curve is banked enough so that the normal force will push the car in the circle and no friction will be required. So in our before situation, which is the perfectly banked situation, the speed is 20.8 meters per second, and our car looks like so. And what we need is a free body diagram showing the forces that are acting on the car. So, at this point, I'm going to ask you to pause the video and create a free body diagram showing the forces acting on the car in the before situation. And welcome back. You should have two forces. One will be the force of gravity, which is pulling straight down as always, and the other is going to be the normal force, which is going to be pointing out perpendicular to the plane of the curve. There is no frictional force because we are looking at a situation where we're looking at a speed for which the curve is perfectly banked. In other words, there's no friction. And so now that we have our free body diagram, the next obvious thing to do is sum of forces. But in order to get there, we need to have some components. And our plan of attack for banked curves in general is that we're going to maintain the usual XY axes. And that may be surprising, because usually on inclined planes we rotate our axes. However, for banked curves, it turns out that rotation is not very helpful, because in the end we are going to be trying to set the centripetal forces equal to mv squared over r, and the centripetal forces are pointing directly along the x-axis in towards the center of the circle. So in this particular case, we're going to keep our axes straight up and down, x and y. And we're going to need to split the normal force into components. So here are the two components, this one and that one. But how do I represent them in terms of an angle? Well, let's come back to our side view. And here is an angle theta, which I do not know. And here's the mg pulling down. Here's the normal force. And if I now draw myself a line like this, you can see that this line is parallel to that one. And if I draw a line like this, you can see that this line is parallel to that one. And so this angle here has to be theta. And since this angle is theta, this one will be 90 minus theta. And therefore, this component right here will make an angle of theta with Fn. Because this component makes the angle of theta with Fn, it is adjacent to the angle theta, and therefore this component is Fn times cosine theta. And that makes the other one Fn times sine theta. Notice that it is opposite to theta right there. Okay, so what we have then is mg pulling straight down. Here's my object. We have Fn cosine theta straight up, Fn sine theta straight in. This allows us now to do sum of forces. And if I do sum of forces in the y direction, then I get Fn cosine theta minus mg, and that sum of forces has to be equal to 0. And if I do sum of forces in the x direction, there's only one force acting, and that is Fn sine theta. And that has to be equal to the acceleration needed to force the car to move in a circle, which is going to be mv squared over r. So we now have our two equations here, and the unknowns for us are the angle theta. We also don't know the normal force, And we also don't know the mass, but we're kind of used to the mass canceling out, so we're not too worried about that. So we have really two variables, two unknowns, and two equations here. And so we have some options for solving. One option is to substitute, the other option is to eliminate. I'm going to choose the elimination route because it shows us a nifty mathematical technique. What I'm going to do is I'm going to divide one equation by the other, and it looks like this. Fn cosine theta equals mg, and Fn sine theta equals mv squared over r. Now, I prefer to divide sine theta by cosine theta, since I know that's tangent theta. So I'm going to take equation number 1 here, and I'm going to put it underneath equation number 2. And I'm going to divide both equations. I'm going to divide equation number 2 by equation number 1. I would like for you to, in just a moment, pause the video and go ahead and do the algebra and see what you end up with. At this time, pause the video and simplify what's left. Welcome back. If you've done everything correctly, you will have noticed that FNs cancel out, and so do the M's right here. And on the left side, I get sine theta divided by cosine theta. And on the right side, I get v squared divided by r divided by g. We know all of the numbers on the right-hand side. We know v, we know r, and we know g. And we also know that sine theta over cosine theta is equal to tangent of theta. So the result is that we can immediately plug in numbers for v, for r, and for g. Let's use 9.8 meters per second squared, just so we can get the exact answer that the back of the book has. And when we simplify all of that, then we can solve for tangent theta. Pause at this moment and solve for theta. Welcome back. If you did everything correctly, you should get theta is equal to 26.6 degrees. This angle right here is the banking angle. And civil engineers would use the same process that we just did right here to solve for an angle such as this, to know how to build the road so that it will be safe at a moderate speed. And that angle or something close, that speed or something close to it is the speed that they'll put on the yellow sign that goes right next to the curve that says curve 30 miles per hour. Well, now that we've solved the before case, what we found out from that before case was the angle at which the curve is banked. Now we're going to use that angle in the after case to find the coefficient of friction needed to keep the car on the road at a different speed at 95 kilometers per hour. Let's take a new page here. So this is our after case. And we're going to have the car again, the mass of M. And now we know that the car is banked at a 26.6 degree angle, like so. And this time we're going to have the car moving with a speed of 95 kilometers per hour, which we found earlier was equal to 26.4 meters per second. Because the car is moving faster than the banked speed, that means it's going to have a tendency to slide off the roadway, in other words, up the curve. And as a result, there's going to be a force of friction that will keep it moving in a circle. In other words, the force of friction is going to be like so. At this time, what I'd like for you to do is to pause the tape and create a free body diagram showing the forces acting on the car. Welcome back. You should have three forces. Two that we had previously, and now we're going to add on to that a normal force that is pushing down in this direction. Just as we did for the previous part, we're going to keep our axes in the x and y directions, and therefore the components of the normal force are going to be exactly as the previous components were. This one is going to be the cosine component of 26.6 degrees, and this one will be the sine component, 26.6 degrees, for exactly the same reason as we had in the previous part. What about the frictional force? Well, the frictional force we can analyze from the diagram up here. You can see that if I draw myself a line parallel to the base, this angle has to be theta right here, and therefore this component is going to be adjacent to theta, which is the cosine component, and therefore my components of friction are going to be F cosine theta, and this one will be opposite, or F sine theta. And I need to remember to scratch out my original F. Now that I have all the forces and all the components, I'm ready to add them up. In the y direction, we have Fn cosine of 26.6 degrees pulling up. We have the frictional force, F times sine of 26.6 degrees pulling down, and we also have mg pulling down. And this sum of forces will be 0 because in the y direction, the car is not moving either up or down. In the x direction, we have two horizontal components. One is friction times cosine of 26.6 degrees. And the other one is the normal force times the sine of 26.6 degrees. Tell you what, let's reverse those so that we can see them more clearly. Fn sine 26.6 degrees plus friction cosine 26.6 degrees. These forces here add up to mass times acceleration, which, as we know, is mv squared over r. And so now we have our two equations, but we have several variables. We have a normal force, and we also have a frictional force. So I could solve by substitution or elimination. That's certainly a possibility. I'm actually going to be slightly more clever than that. First of all, I'm going to recognize that here at the maximum possible speed, the force of friction will be equal to mu times the normal. So I'm going to substitute that fact into both of these equations. The other thing I realize is that cosine of 26.6 degrees is just a number. It happens to be 0.894. And so is sine of 26.6 degrees. It's just a number, 0.447. And I'm going to substitute into there. So let's do all of that. Equation number 1, equation number 2. So if I bring equation number 1 down and substitute the values in, then I get, let's see here, looking for my numbers, 0.894 Fn minus mu Fn times 0.447. And I'm going to add mg to both sides so that I get all of that equals mg. Take a look at equation 1 and double check and make sure that you agree with all the substitution that took place there. And now equation number 2, I'm going to get 0.447 times Fn plus mu Fn times 0.894, and that equals mv squared over r. Now, exactly as we did in the previous part, we are set up so that we can divide one equation by the other. And I'm going to, again, divide equation number 2 by equation number 1 so that I can, well, just so that I can be like the previous problem, really. And when I divide this equation by that one, then the masses cancel. But notice also that Fn is a factor of each of these here, so that it cancels out as well. And what I am left with, when I divide these two, is this equation right here. All of that is equal to v squared over rg, and v squared over rg, when you plug in the numbers, turns out to be 1.24, assuming that we're using 9.8 for g. This is an equation that has now just one variable, and we can either solve it algebraically by multiplying both sides, by cross-multiplying, or we can solve it by calculator. And actually, I prefer doing that. If we solve it by calculator, then we're going to let y1 equal the left-hand side. And we're going to let y2 equal the right-hand side of our equation. And then we'll use second calc intersect to find a solution. At this time, pause the film and find a solution to the equation. The calculator will give this solution as an intersection, and of course x represented the coefficient of static friction. So on our page we will represent that as mu. Now this was a fairly involved problem, and so we wonder, should I be able to do stuff like this? Well, think of this as a stretching kind of exercise. It's pushing the limits of what you can do a little bit. But it ultimately came down to free body diagrams, followed by Newton's laws,